Very warm welcome everyone to our today's lecture. It's my very pleasure to welcome Dr. David Jones from the University of Melbourne, who has won one of the International Excellence Fellowships that were awarded by KIT. It's also my pleasure to welcome Dr. Roth, who heads the International Affairs Office, and she will also give some welcome remarks about that International Fellowship Program.
Well, a very warm welcome also from my side. I tried to keep it very brief. The excellent fellowships of KIT and the grants are a measure within the excellence strategy of KIT. KIT is one of the 11 excellent universities of Germany. And winning this prestigious award affords us not only prestige but also some extra funding. And we are using some of this fund to foster our international collaboration. And the International Excellent Fellowships are a very flexible and a good instrument we can provide to researchers of KIT to easily invite their colleagues, outstanding fellows from abroad, to bring them to share knowledge, to prepare joint research, going into further collaboration and so on. And I'm very happy that Dr. Jones is willing to give some insights into his current research.
Thank you very much for these welcome remarks. I met David already 10 years ago, and that was back in Melbourne. We had an exchange project which was back then funded by the BMBF on the German side and by the Australian government on the other side. And this was back then when Andrew Holmes was still in office. Andrew Holmes is a very famous chemist and later advanced to become the president of the Academy of Sciences in Australia. And that was a chance for David to take over the group. And so he did. So David heads now this group for organic chemistry at the Bio21 Institute in Melbourne. And he has done a lot of very well perceived science in the field of organic semiconductors, in first place organic light emitting diodes and organic solar cells, and so we have taken on this collaboration for about 10 years now, and we're not planning to stop. On the contrary, during the stay of David here in our group, we have found a lot of new opportunities where we can collaborate in the future, and that's what we will do. So David, we're really happy that you're here with us today and that you give us a presentation on materials development for the next generation of solar cells, which is a very exciting topic for us. So the floor is yours. We're looking forward to your talk. Thank you.
Thank you, Alexander, for the kind introduction, and thank you very much, Dr. Wolf and Eleanor, for organising and helping me get here. And so, as Alexander said, I want to talk about materials development. Obviously, this is going to be organic semiconductors and some of the newer work we started and materials I've brought across. I won't be talking about them. There's IP issues potentially. And so the funding for me being here, of course, is from the International Excellence Fellowship. My main funding in Australia comes from the Australian Centre for Advanced Photovoltaics, and they are funded from the Australian Renewable Energy Agency. I also get funding directly from them. Let's get that out there before I go into the talk. The work that I'm going to talk about has been in collaboration with a lot of people, and at the bottom of this is where Alexander comes in. But I come from Melbourne, and so this is the university site in Melbourne, and so the city centre here, and no, this is not the ocean, this is the bay. The ocean is a long way away from here. The institute that I work in is over here, just off this picture. And so that's the biomedical precinct. And so I'm in a bio laboratory or bio institute. So these are the main people that did the work on this. And I'll show you some photos later on. These are the other people at the University of Melbourne we collaborate with. And of course, we collaborate around the world. And so all of these people are on the papers and the work that I'll talk about today. My field, just as a general introduction, goes from materials design and synthesis. We do some basic material characterization, so I'll talk about some of this work later. And so this is something which is the pneumatic liquid crystalline phase, which we found to be very interesting. We also do a little bit on devices, but we don't have the skill set to do in-depth studies. And we're also looking at translation to large scale. So let me start with the image, which is quite bright and colourful. Which gives us a lot of information. So this is a map that was put out a number of years ago, but it's the long-term average solar radiation that hits the ground around the world. And so you look at this map and you see a few anomalies, and you see that Australia should be doing research in solar cells, and we should be employing solar cells. And you sit there and say, okay, Europe and Germany's up in here somewhere, probably not the best place to employ solar cells, but then the southwest of the US, and you've got Sahara and the Mongolian desert. And you sit here and look and say, okay, Brazil's just south of the equator, but of course Brazil has a lot of clouds. It's a rainforest. And therefore this also takes in the day length and cloud cover, and this is the solar radiation hitting the ground. And therefore we should see a lot of very, very large scale development and use of solar cells in Australia, and certainly in the households we have a lot. There are a lot of, now that the cost of solar is coming down, there's a lot of very big projects being announced. And so this is one that was announced recently. This is now a $22 billion project to put solar cells with battery storage over 100 square kilometres of the desert in Australia. So we're going to start using that resource. This is one of many. And so, of course, they're going to put this here in the middle of Australia, and they're going to pipe the electricity offshore. They're going to use the resource. This is one of many that have been announced recently, because the generation of low-cost solar can start driving industrial change. And from an Australian point of view, that means a lot of mining, and people want to make green hydrogen to reduce the ores. And for example, and therefore there's a number of mining industries that want to put green hydrogen out there to drive their chemical processes. So if we look at silicon, and these are the sorts of modules that you can now go and buy. These are state-of-the-art. These are single crystalline PERC solar cells, and this is pretty much a mature technology. And so there's incremental changes in this as they make bigger ingots. They use less silicon for the solar cell modules. And so now the record lab efficiency is 26.7%, and the record for multicrystalline is 24.4 in the lab. And the energy payback period of this is 1.0 to 1.4 years. I read a number recently to say in Munich it's 1.7 years. In the middle of Australia, it's probably less than this 1 year. And so now these are really low cost, and we're still starting to really roll this out on a big scale. The lifetime CO2 emissions of this technology is now around 40 to 100 grams of carbon dioxide equivalents per kilowatt hour, and this is a number that came from the NREL. Okay, so this is the technology that's out there. If we're going to look at developing new technology, we've got to be better than this, and significantly better. The trouble is the numbers are a bit indeterminate at the moment, because our efficiency keeps on changing so quickly. So energy payback period, is 2 to 3 months. We know that that's probably less now, because these numbers were calculated when a couple of years ago, when this efficiency was only about 12-14%. And so we're getting better all the time. And Heliotech here in Germany put out some numbers recently of 3 to 15 gram carbon dioxide equivalents per kilowatt hour. So we are environmentally a lot better if we can roll the technology out on a large scale. So that's what we're trying to do. I'm trying to do, make new materials to make that happen. So why organic? And so the big reason for organic solar cells or organic semiconductors is that we can make lots of changes by changing the structure of the organic molecules. We can change quite easily the optical and physical properties over a whole range. We can't do that. If you've got silicon, you've got a banger. Whereas with organic semiconductors, we can change the absolute energy level as well as the relative energy level by changing the structure of those materials. Okay? And a lot of these materials are already commercialized. So it's then taking what's already in the industry and being able to modify it for the sorts of materials that we're looking for printed solar cells effectively. And so we know that we have a lot of OLED devices. We now have lots of companies bringing out flexible screens. So this is a technology which is related. So instead of putting light in to get electricity out, we're putting electricity in and getting light out. Okay, so they're the opposite sides of the same coin. And so my job is to make new materials and make them work in solar cells. So I want to touch on three areas in the talk today, very, very high level. But the first is looking at solar cells, is basically saying, how do we make a solar cell? So we take a mixture, a solution containing a mixture of this P and N-type organic semiconductors. We make a solution, therefore we can print it to get a bulk heterojunction. That's basically a mixture of these two materials, the P and the N-type organic semiconductor. And then normally we need to post-deposition treat it, so we can heat it or we can put a solvent in there to change its structure. The trouble is, in doing this, what we're actually doing is kinetically trapping a structure which can then later on continue to evolve. If we over-anneal it, we get too big a domains and the device doesn't work. In operation, the structure can continue to change and therefore we can lose the efficiency of the solar cell. So it's this kinetically trapping that we want to look at and see whether we can change how we structure that. And of course, in doing this, we also want a network of bicontinuous phases. We want to be able to get the charges out of either the P-type phase or the N-type phase. So we need continuous pathways for the positive or the negative charges to get the electrodes. Okay, so another couple of things we're looking at, of course, is we want to tune the electronics at this interface. Very quickly going through how these solar cells work. We absorb light and we generate an excited state. This is an exciton, a coulombically bound electron hole pair. And therefore this diffuses to an interface. And because this has a binding energy, it takes energy to break it apart, we need an offset between the P-type material and the N-type material, okay, the donor and the acceptor. And so this is where we get separation of charges. Okay, there's a lot of work now going on to say that we can reduce this offset, but let's say that it needs to be an offset there. So we need two materials. And so we can tune the electronic coupling at this interface in this bulk heterojunction by deposition, by post-deposition treatment. So I want to look at one class of materials that we've been looking at. And this is one we looked at for a number of years. And this is our BXR series of materials. And so we got into this simply because we thought we could change the structure to improve the crystallinity of this material. So that's how we got into it. And we can certainly do that. That was the first paper we published back here in 2015. We extended it. So all I want to talk about today is basically extending this central bit and looking at n is equal to 1 or 2. Okay, so all the other stuff we've done as well, but I don't want to talk about that today. And so we've had a lot of publications on this, looking at the structure, looking how the structure evolves, looking how then the devices perform. And so something which we really were looking at. Okay, so very quickly, if we make a device, so we put this mixture of BTR and PCBM in here and make a simple device, we can then look at the efficiency of turning those photons into charges. And so as cast and then annealed, works okay. We get a reasonably good device here, and if we look at then on another device and look now at how efficiently we turn those photons into electric charge and get rid of all the reflections and everything else, we're getting about 90%, which is very, very good. And so these worked really well. And the other thing we can take away from it is they have excellent efficiency. This is back in 2015. They also worked in thick films. And this is very, very important because if you are printing a solar cell and your printing thickness varies, you don't want that to impact your overall efficiency of your cell. So you want that to, if you can print thicker and you've got a variation of, if you've got 300 nanometer and you vary by 50 nanometer, you go from 300 to 350 down to 250, you probably won't change the efficiency of your overall cell. If you've got 100 nanometer thick and you're going from 100 to 150 down to 50, then you probably have issues. And so having thick films was really important. And this is a material that's highly crystalline, has a number of crystalline phases, a high temperature nematic phase, which means that it's quite ordered when it first starts crystallizing. And so this is a busy slide, but this is where I want to take you through the overall summary of all the work we've done. And that is work, and this is work that Kyra did and she published this year. and she was at Princeton when she did this work. And so if we look at that, as cast films, we get pretty poor devices. If you look at these voltage current curves, they're not really good, they're not very square. And so if we look at the model of what's going on in the film, we see that we've got a mixture of the donor and the acceptor, the P and the N-type organic semiconductors all over the place. And then we summarize what's going on in this device. And so there's a lot going on. And so we excite it, and then we have charge separation, and then we generate these two polarons. Okay, just positive and negative charges, depending on what field you come from, how you refer to them. They can be positive and negative polarons, they can be radical cations, radical anions, or they can just be charges. Once we get here, we also can recombine these charges to get what's called a charge transfer state. And if we generate the charge transfer state immediately, it'll be a singlet. If we recombine charges, it can also be a triplet. That just is talking about the spin configuration of these. The electrons are either both up in a triplet or up and down in a singlet. Okay, and if we look at this, we see that in the unannealed film, we must be generating triplet CT states, charge transfer states, because we populate the triplet level of the donor. And that's a loss mechanism. And so that's what we don't want to have happen. However, as soon as we anneal the film, what we end up is getting very, very pure domains from all the data we've got, small domains, and we get very pure domains. Now what happens is we get this electron, we generate these electron and holes, and they stay there. And so when we look at this, we then go through, and this is all the device work, small pure domains. But we can estimate what that charge recombination rate should be, and we are recombining 2,000 times slower than we should be. And so this is really unusual. That means we can get bigger numbers for our device efficiency. The other thing is that the thicker the device, and so that's the data here, and you can't see it very well, but going from 90 nanometer thick film up to 320, we get a better device the thicker the film. And so we need to understand that. And so Kyra did a lot of really interesting work, some really interesting numbers, and showed that we actually get a really large buildup of charge. These act like capacitors. Phenomenal charge buildup. And it's actually the charge buildup, we think, which stops the charges recombining, because it generates a secondary field which polarizes the material in between it. And so we get really high charge buildup, really high voltages across smaller distances, and we get low recombination rates. And these work really well in devices. The couple of the postdocs we had working on these materials to start off with, they've gone away, set up their own groups. They now have been modifying these, and they're the best materials with non-fullerene acceptors if it's all small molecule devices. They work really, really well. But we're not controlling our domains very well. So what we want to do is to see whether we can get rid of this whole process of having a kinetically trapped device. And so can we control morphology through the development of a bottom-up? Okay, control our chemistry to actually control the domain size, control the phase separation. And so that's what we want to do going forward. Okay, and so for organic semiconductors, the issue that we have is that when we are making this, this blend, we really need to have the free energy of the two materials very, very close. Because if we don't have it close, when we try to make this junction from the blend of the two materials, they'll phase separate, and therefore we won't get a very good device. So we actually have to have a very, very similar free energy of the two materials. So can we use block copolymers to do this? If we've got block copolymers, we tie the two types of material together and we remove any possibility of having really large domains. So we've been working on this for a while. The chemistry is very, very complicated, but we're now making progress. And I just wanted to touch base on that. And so if we basically have a donor, the P-type semiconductor, and the acceptor, the N-type semiconductor, now we tie them together, we can self-assemble, and we should get an ideal type structure. So we've used a bottom-up approach to control the phase separation in these materials. So my PhD student Valerie went through, she did a lot of chemistry, she did a lot of work, and so she made this polymer. So this is a very, very common polymer. P3HT is a P-type, and this was the N-type organic semiconductor, now with oxygens to differentiate the free energy of these two blocks. If you look in the literature, you'll find that when people have done this work before, they don't have pure di-block copolymers. They don't have a block of A and a block of B. They've got a mixture of everything. They've got a mixture containing the homopolymer of the donor, the homopolymer of the acceptor, and maybe tri-block copolymers, and you have no idea what's going on when you actually make a device out of those. Having this handle, we were able to purify this di-block copolymer really, really well. Then when we made a thin film, we were able to show that if you've got a blend, it doesn't work. If you have a blend of the di-block and the homopolymers, it also doesn't work. But when you have the pure di-block, you get really good control of the morphology. And so this was basically a proof of principle to say that you can use a di-block copolymer where you've changed the free energy, make one hydrophobic, one hydrophilic, to control that phase separation. But these were not really good materials. This was just basically going on what we had before. So we wanted to change the materials, okay? And so I'm a chemist. I put up a chemistry slide. This is your synthesis for today. I don't want to go through it, it's okay. I just want to highlight a couple of things out of this, okay? Now, we had to search very, very carefully for a catalyst to do what we wanted to, and this is Guggendeep's work, and we had to do a lot of synthesis to get a monomer which we could polymerize to get a lot of control over that polymerization process. When we do that, we can then form a polymer where we have the N groups, which are highly controlled, and we can actually add functionality to be able to do the next step of what we want to do. And so when we look at the mass spec, we see that these are really clean. We have real control over these, this polymerization, and we can control our molecular weight very well, molecular number. And we were aiming here for 10,000, we're at 11,000, that's very good. Okay. So what we need to do to push this chemistry forward is to actually make these asymmetrically functionalized push-pull monomers for both the P-type and the N-type semiconductors. So Guggendeep's gone and done that. We've showed you this one. So this is an electron-rich, electron-poor, push-pull. And we have different functionality on both ends. So that's the asymmetrically functionalized push-pull monomer, one for the P-type organic semiconductor that we're going to make and one for the N-type. And Guggendeep would be really annoyed with me skipping over all his chemistry, okay? So he spent 2 years getting that to work. And so then we take these and we can then put them together, we get a polymer. Now a block of the N-type and a block of the P-type. So we've got to where we want to be. But we've done it in a way that we now have a toolbox. So this is incomplete work. The first paper is on my desk. I need to go through it to see whether we can submit that this week. But we have a toolbox. So we have now a method of polymerizing an asymmetrically push-pull monomer to one, in really controlled polymerization, control the block length. If we control the block length, we can control the domain size. We can also change the amount of oxygenation on the side chains here. We can change the free energy difference between the blocks and therefore force phase separation. And therefore we should be able to push it so that we get really good phase separation. And the little bit here in the middle, it's only small in this one, but this is the linker. And so we can substitute this linker to effectively control the energy landscape between the two blocks. And so we're now set up. If we hadn't had COVID, we would have finished some of that work now, but we're now set up to be able to really look at domain size, energy landscape at the interface on the performance of these solar cells. So that's work still to be done. Okay, want to go off on a different track now. It's the work that we're doing a lot with and the materials I brought across to Karlsruhe. So how do we improve the efficiency of a solar cell? So this is going back to the basics, okay? We absorb light of all, or we have light of all wavelengths, and we have a semiconductor. So we have a valence band, conduction band, and there's a gap in here, which is not populated. So we have a band gap in these inorganic semiconductors. And so if we have a photon of light with the energy which can't promote an electron from the valence and conduction band, it's not absorbed. So any energy is lost. If we have a photon which is at or above that gap, it will be absorbed and we can generate an electron in a hole. Okay. And of course, anything which has got excessive energy is going to create an electron in a hole, and then we're going to lose that excess energy as thermalization. We're going to lose energy, it's going to heat up the solar cell. So this is really lost energy in a solar cell. And so we can look at that in this image that I took off the web. And so we can summarize that. So basically, and this is the band gap for silicon. And so anything below the band gap is not absorbed. So those photons we can't use. Anything above the band gap, we will absorb. We will generate one electron hole pair per photon at best. But that means that all that extra energy is lost. And so that's that grey bit here, the thermalization. So we should be able to try to use this. And of course, no system is perfect, so we have extraction losses, which we can't do anything about. And so obviously, you can improve the efficiency because the voltage of this cell is going to be dependent on this band gap. And so you can say, okay, I'm going to split up the solar spectrum and get solar cells of different band gaps, different voltages, therefore different efficiencies at the same current if we absorb the same number of photons. And so in the literature now, the best research lab is stacking 6 solar cells on top of each other and you get a 47% solar cell. 43% solar cells are commercially available. They have 3 solar cells stacked on top of each other. I wouldn't run out and buy some to put on your roof. It'll cost you about 30,000 euros per square metre. Okay? You don't put them on your roof. You put them on a satellite. Okay, so, but there are other ways of doing it. And so we can do things called up conversion, down conversion. Okay. And so if you look at these photons below the band gap of silicon, if you can combine the energy of 2 of these, i.e. up conversion, you can generate a photon or an excited state in the silicon, which you can then improve the efficiency of the silicon. Equally, if you have a photon which is twice the band gap, maybe you can make 2 excited states out of it, and therefore you can get 2 charges per photon, and therefore increase the efficiency up here. If you look at the theory of that, you can take a 33% efficient solar cell, this is theoretical maximum efficiency, and you can go up to 45. Depending on your calculations, there'll be a little bit less on both ones. So in theory, if we can do this down conversion, we may be able to get up to 12% efficiency increase. If we think back to those commercial solar cells, we're not looking at getting a 12% increase. We would like to target a 5% increase. But that's an absolute 5% increase, and therefore that's a 25% increase in power per solar cell for the same cost effectively, if we can do it. So that's the driving force of why we want to do this. So this, for us, is called Singlet Fission. There are other ways to do it, but we're looking at Singlet Fission. So this is the work that started in my group with Cigar, and she finished a PhD and she's now got a fellowship looking at Singlet Fission materials. Okay, so this is where we need 2 chromophores. So we have 2 molecules that we're going to use. In the first molecule, we excite up to the singlet state, and we use that energy if we've got a triplet state, which is half the energy of the singlet, and then we need another molecule, and we share that energy between 2 molecules. And so what we're doing now is taking 2 molecules, one in a ground state, one in a singlet state. We're sharing this energy between these 2 to make initially a correlated triplet pair. Okay, so this is a very advanced process of basically forming this coupled quantum coupled state. And so we get a correlated triplet pair, but this is allowed from spin theory. And then after time, we can relax and get 2 isolated triplets, which we should have the ability then to harvest and double our current for these high energy photons. So this is what we're doing. What materials can do this and how can we incorporate them into solar cells? I don't have all the answers for that, but this is where we're going at the moment. So if we look at what's in the literature, and so things that do singlet fission, polyacene, so tetracene, pentacene, oligophenols, these diphenylisobenzofurans, these carotenoids and these rhylenes and some conjugated polymers. But because we need two molecules close together, we need highly crystalline solids. And so effectively, the singlet fission yield is really dependent on the crystal packing because we need this overlap between the orbitals of the two molecules. However, that doesn't always work well because it also then depends on the polymorph. And so most of these materials up here, they may have two polymorphs, and this is the diphenylisobenzofuran. One polymorph or one crystal structure is singlet fission active, the other one isn't. So then we need to be able to control the crystallization of these materials if they're going to undergo singlet fission or promote singlet fission in a solid state. Now people have been looking at that and said, okay, we need two molecules, let's join them together. And so a lot of people have been doing a lot of work. So this is the pentacene, tetracene, join them together, see how singlet fission works. And we can do that with the diphenylisobenzofurans and all these other materials, putting bridges in. Most of this work has been done in solution. If you try to then look at these in solid state, they're no longer singlet fission active, or the singlet fission activity is very, very low. So we don't get that benefit. So when I came into this work a number of years ago with Cigar, we basically said, what do we need to change? And so we said, okay, we want to ensure that these materials undergo singlet fission in the solid state. We want to be able to control them, solution process, so we have to have them self-assemble so we can control how they assemble so we don't get different polymorphs. We want to be able to control with our inter or intra, so if we have a bridge that's intramolecular because we have these two molecules that we're going to put these triplets on in the same molecule, and we want to be able to energy match the material, singlet fission material, to the underlying solar cell. And we also want high molar absorptivity. We want the actual material to absorb a lot of light for a thin film. Now that's a problem in the current generation of materials. So if we look at something like pentacene and we say, okay, this is the solar spectrum and we have a 100 nanometer thick film of pentacene, it'll absorb this much light. 500 nanometer, this much light. To absorb all the light that we want to do the singlet fission with, we need a layer which is 1 micron of tetracene and 1 micron of pentacene. But of course, we have issues with that, and this is because we have low molar absorptivity. The triplets have a short diffusion length and a short lifetime. And so if we have a film that thick and we generate a triplet at the top, we'll never be able to collect it at the bottom of the device because it's just too thick. And so if you look at most of the devices in the literature where they say they do singlet fission and they have really good external quantum efficiencies, i.e. they're getting more than one electron per photon, these are, I don't want to say manipulated, but basically they are calculated by having a very thin film and saying of the light absorbed, we are getting 120% efficient collection. But they're not absorbing all the light available. And so we have a long way to go. So we wanted to change that. Okay, so we wanted to basically use this sort of a structure, and we have this core here, which is going to be driving our self-assembly. We wanted to have some sort of linker or a bridge if needed, and we wanted this acceptor or this triplet host. This is where our triplets are going to end up. So we wanted this structure so that we could have then some self-assembly. Intramolecular singlet fission. Okay, so we went back and thought about what we can do. We knew this core was in our materials I talked about earlier. This promotes strong self-assembly in those materials. Tried it with this diketoprolyl, which is a very, very well-known singlet fission material in solid state. Let's link them, see what happens. Measured the singlet and triplet energy. They are about right, so that's all right. And then we looked at it. And Although we saw evidence of singlet fission in solution, in solid state we didn't see any. And therefore our crystal packing is not right. So we had to go back to the drawing board and say, okay, this core isn't giving us singlet fission, it's not giving us the self-assembly. So we need to change it. We need to change that core to say we need something which is going to drive self-assembly like you wouldn't believe. We then wanted to increase the S1 energy if we could, and we still wanted to call it solution processable. So we thought about what we could do, what we could change in that core, and then we realized we'd already done it a number of years ago. We'd already published it a number of years ago. We used this material as a donor in organic solar cells, and it wasn't very good, let's face it. But we have this hexabenzocoronene, and that really drives self-assembly. We now have a fluoronyl bridge, but we have the same singlet fission material at the end. And we know that they pack in columns because we'd done all that work, we knew that work, and therefore we basically went back and said, okay, we've got this material, is it a singlet fission active material? And so a little bit more detail, we know it self-assembles, we can see that in solution, we can do NMR, and we can see that these peaks here shift a lot. We can extract association constants from this data, and we can see that it stacks through this hexabenzocoronene in sort of columns. And so then we did some X-ray work. This is grazing incidence wide-angle X-ray scattering that we did at the Australian Synchrotron, and we look as cast, and we basically see no structure. Sorry, this is not a very good image. We don't see a lot of structure here. So if we have crystallites, they're too small to diffract. However, when we thermally anneal, we start getting peaks here, and there are a few peaks here. Again, sorry, the image is not great. We can index these to hexagonally packed columns. And we can tell by the pi-pi stacking peak here that they come out of the plane. So they have everything we really want. And I'm not going to go into all the really high-level transient absorption spectroscopy, but when we measured these, the triplet yields for the as cast was 150%, and the annealed was 170%. So our first attempt at this gave us really good yields, singlet fission yield, in the solid state for this self-assembled core. Now, if you think about singlet fission, you're generating this excited state. Normally, you would expect a material like that, hopefully to undergo fluorescence, and therefore you'd have a long fluorescence lifetime. And however, if you have singlet fission, it means you're taking that singlet state and generating all these triplets, which are going to be lower emissivity, and therefore you should fundamentally change your fluorescence kinetics. And so these are the absorption profiles, emission profiles for the solution and then thin film for this material. And when we look at the fluorescence lifetimes, we see that in solution, we don't see a lot of change from the isolated chromophores. However, in thin film, we really kill the fluorescence. And if we model this, then it's a by exponential function. And so we've gone through and we've done all of the hardcore transient absorption on these, and we can identify the species and see what's going on. Okay, so where does that leave us? When Cigar finished this work, or slightly before, we applied for some money to do the next generation of materials. So how do we incorporate singlet fission materials into devices? So if we look at one type of silicon solar cell, this is the interdigitated back contact solar cell, so all the electrodes are at the back, they have a textured surface for light harvesting. Then we sit down and say, okay, this is the perfect device for incorporating singlet fission materials. Because we can flatten the surface, lose a bit of efficiency, but this is micron scale roughness, and we want a 100 nanometer thick singlet fission layer, so we need to get rid of that initially. So this is the device architecture we're looking at. So we've basically got the solar cell, silicon solar cell, and therefore that tells us we want to change our triplet energy level to energy matched silicon. So we need to design and make that, and we've done a lot of that. We need a passivation layer here, which is not going to destroy the function of the solar cell, the silicon solar cell. and then we're going to put our Singlet Fission layer on the top. So now instead of both the low energy and the high energy photons going into the silicon, the low energy photons will go straight into the silicon solar cell. The high energy photons will be trapped by our Singlet Fission material, will generate triplets, and then this passivation layer is very thin, and we can do energy transfer into the solar cell. Okay, so this is what people have demonstrated before, but they had a very, very thin film and really poor light absorption. People also do a similar thing. They take the triplets and they transfer the energy to something which is going to emit light, so a quantum dot or something, and then they emit light, and then that light is reabsorbed. The trouble is your Singlet Fission has to be very efficient, your triplet energy transfer, your transfer of energy has to be very efficient, and your emission from your quantum dot also has to be very efficient, knowing as soon as you do this emission, 20% is going to be lost through the top of the solar cell. And so people are doing that. The trouble is you have so many lost pathways. And what I'd ultimately like to do is to actually incorporate the Singlet Fission material into the solar cell. But that has its own problems. One is you need to energy match both the absolute and the relative energies on your new material. So what we're doing now, and I can't talk about it because it's ongoing work, we're now designing and making new energy matched Singlet Fission materials, energy matched to silicon, and we've got a big program to do that. So we also want to energy match these Singlet Fission materials to other types of solar cells to see whether we can enhance the efficiency. One of the issues in more general is that the triplets are hard to harvest. And so how do we harvest those when we're looking at new triplet fission or new materials to harvest the energy from those Singlet Fission materials? So that's what we're looking at the moment as well. So at the end, just basically Cigar did the Singlet Fission work and has now got a fellowship to work on the characterization of new materials. Calvin did his PhD in my group and also got a fellowship to make new Singlet Fission materials. Paul and Calvin did a lot of the work during their PhDs on those first materials, the BTR, BQR type materials. Valerie started the block copolymer work. She's now a beamline scientist at the Australian Synchrotron. And Gagandeep is coming up to the end of his PhD, and he did all the development of the new block copolymers. And Jeg is in my group, and he does all the devices for us, and he's happy he's got a brand new glove box to do Singlet Fission devices in. So I want to thank them, thank you, and thank the funding agency for getting me here for this talk. Thank you.
Thank you very much, David, for this wonderful presentation, and I think you all got an idea of why we have David here, because David is not only an organic chemist, he also is at the interface to material science, to understanding materials, to understanding devices, and that's what you need when you work together with a chemist. You need a common language at this interface between the disciplines. So I'm pretty sure there are questions for David, and so this is your opportunity to not have to send an email to Melbourne, but to just ask right away.
You can send one to Melbourne, it's going to bounce back either.
Maybe I start with a question. It may sound a bit silly, but I've been a couple of times to Australia, and I know that kangaroos can be a real problem. So if you want to deploy solar power plants at this scale, do you have to worry about those guys?
I would worry about the camels. They're bigger.
Okay.
It's something which I haven't heard anything about. Obviously, there are already some arrays out there. I think your biggest issues, I mean, a lot of people use solar arrays because they actually get shade for growth of crop and everything else underneath them. I think it would then depend on what you keep out and what you let in. And then keeping them clean is always an issue.
Okay.
Yeah.
So maybe a bit more scientific question. So
yeah.
you said that you would like to staple your molecules that do the Singlet Fission. So, but we all know that if you have pi conjugated molecules and you stack them, you will usually change the energy levels. Is this a problem or not? Or maybe does it even help?
No, in essence, what you say is correct. However, the triplets tend to be very localized. And so with all the changes we've done, so we went from the benzodiazepine core in our first group to this hexabenzochoronine and the linkers, the triplet energy didn't change. And so because it's very localized. And we think that's one of the reasons sometimes it's very hard to separate the charges from a triplet, because they are very localized. And therefore we've used that in the design of our new materials, in that we can do a lot of other stuff. But if we know what the triplet energy level is in the molecule and it's been reported, we don't expect that to change much when we adapt it by putting it onto this linker that we're using. There's a number which I don't know for these materials. Some of the early work we did here just on the core. So if we go back to the core of this molecule, let me go back one more. So we did a lot of work initially trying to understand what goes on, and that was work we did some stuff here at KIT in Dagmar and did some TEM work, and we actually were able to measure some of the crystallite sizes of this material. But we don't have that data for this whole material, so I can't tell you what we've got. But we're looking basically for 100 nanometer thick film, and I've got a new postdoc that's looking at the question of how can we align these things consistently, and can we basically get 100 nanometer thick homotropic alignment. No, that's what we want to try to see whether we can get. We probably won't. Yeah. But then it's really a matter of, once we've got the triplets separated and free, then how easy is it for those to diffuse through? We think that we should get pretty good diffusion, especially if they are in general aligned homeotropically. Yeah, it's something which we haven't looked at that in these ones, but Calvin during his PhD did some other work. And we showed in that work, just by looking at a lot of variable angle GWACs, that you can control the orientation of some of the crystallization by controlling the solubility. And so what we think is happening there is, if you have something which is not very soluble, you tend to get nucleation and crystal growth at the high concentration interface, which is the air solvent. Whereas if you get something which is really soluble, you tend to get nucleation and crystal growth a lot later, and you can have the internal or the bottom interface then controlling some of the growth. And so if we had more soluble materials, we tended to have more face on packing of our materials. And so certainly in the literature, if you have a capping layer, so you stop that, you tend to be able to get homeotropic alignment of your crystallization. Okay. And so we're looking at that at the moment. Penacene we don't use because it's air sensitive and it doesn't have enough absorption anyway. All of the chromophores that we've been looking at, and so for example in this, the diketopolypyrrole, this one's got a slightly lower energy, but it should potentially sensitize oxygen. It doesn't. We're now looking at ones where we have 1.2, so triplet energy levels, and we do everything in air. So these are all air stable. They may interact with oxygen, but they don't get oxidized by oxygen. And so we don't really want something which is so air sensitive that we can't use it. So we're looking for chromophores that are inherently stable. There are a lot in the literature, and we're using those, and we're also designing our own chromophores. Yep. So yeah, so all of our current materials are all worked up on the bench in air, and they're all stable. It depends on what sort of stability you're talking about. One goes back to what Stefan just asked. I mean, a lot of the degradation is the fact you get moisture and oxygen coming into the solar cells, and therefore you get those secondary reactions. And therefore that's encapsulation, and therefore we encapsulate normal solar cells, so that's not that different. We already encapsulate the OLEDs, and so we just need a slightly better encapsulant or a more robust system. The second bit is basically physical degradation, and you really won't change that until you change the stability of your solar cell. That's why we're doing the block copolymer work. Because if you think about block copolymer work where you're actually driving the phase separation by having an amphiphilic block copolymer, the only thing you can do if it changes physically is to get better. Because you're actually going to drive it to a more stable system. You're driving it towards a thermodynamic minimum, and that'll be the completely phase separated system. So under those circumstances, your device should get better with time because you're going towards, you're driving it towards that thermodynamic minimum. Does that answer your question? Yep. That's one of the reasons we do it. We want to understand domain size and whether that really is as important as what people say, but also to have that bottom-up approach to have really clean domains. It depends. I mean, if everything around you is burning, these will burn too. The thing is, yes, they're flammable, and so the other side of it, of course, you may be also asking about the electrical testing you've got to go through, and so we're going to have to go through all those testings. These will be flammable, but they're going to be encapsulated as well, and so they're going to be no different to what, glass on a silicon solar cell. We talked about that for a number of reasons. The other thing is that if you've got a solar cell which can float, then you can also, in hot areas, stop evaporation of ponds, lakes, etc. in theory, and therefore protect it in that way. Your water may get a bit hotter. And so people have looked at that, but of course then you have the secondary problem. You're putting it in one of the things you don't want it in. And you're basically putting it on top. And so you're going to have to be reasonably careful about what you do. And then all of the electrical connections. And so, yeah, these are effectively the doldrums, and therefore people have thought about it, but there's a lot of land here and some other places which is not very well covered. And if you go back to a lot of the original predictions, it's a terawatt problem. We need a lot of energy. And so back a number of years ago, it's probably less than now, they said that we needed 6 squares of 100 by 100 kilometres, and that would power the world. Okay, so it's not that much area, and there's still a lot of land to use.
I didn't realize that.
Yeah, and so as the solar cells are getting more efficient, that area gets lower. But effectively, because we want terawatts of energy, the actual land area that you need to cover is not that large. And so we're already talking about a 100 square kilometre bit of Australia.
And there is nothing in the middle.
And there's, that gets into a political question. I'm not going to answer that question. We're dealing with 200 odd years of history there that is very political. But there are lots of areas where it's suitable, yes.
And how does Australia want to export that energy? Probably not by cables. Is it hydrogen?
It's hydrogen. Yep. So, there is that cable that they are expecting to put a cable, but
not for the entire world.
No. Yeah. And so, but people have said we can put a system here and a cable across to Europe.
But you have a cable to Singapore, is it?
Yeah. That's what they're planning. And so, at the moment, a lot of the new plants are to supply really power-hungry industries like the mining industry. So one of the mining companies says, we're going to supply all our power through renewable. And they've recently said, the same company has recently said, we're going to offset all of our exported carbon dioxide. So if you're thinking about, from an Australian point of view, exporting iron ore and carbon, iron ore from Australia, 2.4 million tonnes a day of iron ore. 850 million tonnes of iron ore a year. Okay, if you then look at that as far as the carbon dioxide into the air, it's about 750 million tonnes from Australia. We don't count that because that's in our exports. But one of those companies says they want to offset that by getting green hydrogen and then selling the green hydrogen as a way of offsetting their exported carbon dioxide effectively. And so those are the things that are now on the plans for Australian industry, and I expect a lot of those to be built.
But the truth is also, if you convert it to hydrogen, you need much larger areas of PV because that process is not as efficient as we wish it to be.
Yep.
So then the area will probably be a bit more. Okay.
What Gagandeep has struggled with for a lot of his PhD is how to make those materials, the asymmetric, the functionalized push-pull monomers, but also how to make them for both P and N-type. And so if you look at a lot of the really high-performing polymers, there is no reason why we can't modify those monomers to then start tuning that. The other side was looking for a catalyst which gave us what we call a pseudo-living polymerization, so a really controlled polymerization. And so, like anything, we think we've got a good system, but if you come to me and we try it and it doesn't work, we'll have to find a new system. And so what we want to do at the moment is really to probe the system we've got, or the next good system, to sit down and say, you know, we talk about this domain size, we talk about this domain purity, we talk about all these other things, and we talk about the interface energy landscape, but we really don't have a toolbox to be able to look at that. And so what we wanted to do was to get a toolbox to say, yes, we can do this, we can then design these really pure domains here and here, and we can then put in this energy landscape. The only thing we don't know is, you know, how just slightly disordered that energy landscape will be as we go through it. But at least we're going to get closer to what people say that we should have, and we haven't been able to build that before. So that's where we want to go with that. So looking at those fundamental studies.
So you've seen today a lot of interesting science around the development of new molecules, and you have also got an impression of our collaboration, I think, and you see that there's a very low threshold in approaching David. If you have your own scientific ideas, what goes into this ballpark here, please feel free to contact David or myself, and we will be happy to discuss with you about this. Thank you for joining us today. Have a nice evening. Bye-bye.